Anybody have any questions from homework or anything? I don't have the tests done yet, but I'll have them by Monday. Yep.
For the number 9,
Yeah.
this guy,
Yeah.
you said it at the B, tension for 0.25 meter from a light end, so it means cut it here?
Yeah.
Okay, got it.
What? Number 9?
Sure. You want me to do that example?
Yeah, I mean the distance of x half to prevent the movement of inertia at the second half. So there is a weight.
Have you taught us this? Do we know this? Or am I
No, you don't know how to do that.
Right.
That's in the. Oh, okay. No, that's the next thing we're doing. That just found its way into the wrong set of problems. Sorry. Yeah. Okay. Now all the mistakes in those problems are behind us. That was the last one. Okay, so now that we're done with internal loads in beams, and now we're going to use those to calculate stresses in beams. And the way we're going to do this is we're going to break up the total stress into the stress due to tension compression and the stress due to the bending moment and the stress due to the shear force and the stress due to torsion. And for each one of these, we're going to assume that the other type of loads aren't happening. We're going to calculate it, we're going to calculate these stresses as if the beam was in nothing but tension compression. Then we're going to calculate the stress as if the beam had nothing but pure bending, then shear force. And then when we're done, we're just going to add up all those stress tensors. And there's nothing... So you might think rightly, well, maybe material that's under tension compression behaves differently in bending than it does if the material isn't in tension compression, right? I mean, there's these complicated interactions going on. But our ability to break it up into the sum of individual internal loads is called the superposition principle. PLE. And it depends on the linearity of the relationship between stress and strain and on the small deformations. So it's not true in general, but it's true in this class and in most analyses you'll have to do as an engineer involving stresses and strains.
So we want this thing to go back to its normal shape and form when we're done. When
Yes.
no force is applied to it internally or externally.
That's right. If you ever have, for anything in this, any of the techniques we're using in this class, if you're analyzing a load that leads to a permanent deformation, then you need other techniques that we're not talking about in this class. And most of the engineering applications that you'll ever do will involve the elastic range, so you won't have to worry about that, but it's a good thing to keep in mind. But there are, you can come up with elastic deformations that don't follow the superposition principle. That would happen if you had nonlinearity between stress and strain, like rubber, or if you had big deformations, like, I guess, rubber again. Like rubber's elastic up to, take a rubber band, it's still elastic at 4 times its original length, you know. You're still in the elastic range, but you couldn't use the superposition principle because you have really big deformations. Okay, so we're depending here on linearity and small deformations. So we're just going to go through stresses due to tension, stresses due to bending moment, shear force, and torsion one by one, and then we'll add them together in a real problem. So the first one, the easy one, is stresses due to tension compression. Well, really, we already know how to do this one, because if we're going to act like the member is in pure tension compression, then that's an object being loaded according to the rules of a stress element, and we already know how to deal with that. So the stress along the axis is just equal to let me write that as T, the internal tension divided by the cross-sectional area. So as an example, let's say we have a beam with a 8,000 Newton force applied to the left, on the left end point, and at the midpoint, a 2,000 Newton force this way, and then here a 6,000 Newton, so these are both Newtons. And I don't have this in the problem I'm looking at, but actually let's apply a downward force too, just to sort of clarify what I'm talking about with the superposition principle. So let's say that there's also a torque of 1,000 Newton meters. And at the midpoint, let's say that there's also a torque of 1,000 Newton meters. And the downward force, let's say that's 500 newtons. And let's say that we want to calculate the, and actually let's move, sorry about this one. Let's move that torque to the end. So we have a 1,000 Newton meter torque going to the right that's at the right end. Yes, we do. Thank you. So let's say there's 250 there and 250 there. Otherwise, that's just accelerating down. And let's say that we want to calculate the stress tensor due to tension compression halfway between the middle and the right end. So what's the stress tensor due to tension here? And I'll use a coordinate system with the x-axis along the beam, the y-axis up, the z-axis out towards us. Okay, so the first thing we have to do is calculate the internal loads. We need to figure out the internal tension. And since we're asked for the stress tensor at a specific location, we might as well just calculate the internal loads at that location instead of coming up with the functions for the whole thing. So we'll cut it at the dotted line. And so the loads we have acting on this isolated piece are a 1,000 Newton meter torque to the left, an 8,000 Newton force to the left, 250 up. Then at the midpoint, we have a 2,000 Newton force to the right and a 500 Newton force down. And then we have the internal loads: tension, shear force, bending moment, and torque. So Newton's second law says negative 8,000, 0, plus this one I'll write as positive 2,000 in the x direction, negative 500 in the y direction. And then we have t negative v at the cut, and that's equal to 0. So t is equal to positive 6,000. Yes. Let's put that in this one. And the shear force is negative 250. And then before I go on, I forgot to give the cross-sectional area of this. So let's say the beam has a cross-sectional area. This would have to be given as part of the problem of 0.001 meters squared. And then the moment equation about the z-axis says we have the downward force of 5,000. Did I give a length of this? No. Stupid idiot. Okay, so let's say this is half a meter. Okay, so the moment about z produced by that 500 it's a moment arm of a quarter meter times 500, and that would be, if this is the about point, that would be a clockwise rotation. So that's negative 125 plus m minus v times, I guess that moment arm would be 0.375. Is equal to 0. So m is equal to, what's 250 times 375? Times 0.375? 9075? 9375. Okay. What? Because in this case, we're not, this is x, but in this case, we're just doing a cut at a known value of x. X is equal to 0.375. So that's why. Okay, so
the 125, negative 125 came in-house, sir?
That is 500 times 0.25. This distance is 0.25.
Okay.
So we have negative 93.75 plus 125. So what's that? 131.25. 31.25. And then the rotational equation about the x-axis, we have negative 1,000 plus fancy t is equal to 0. So the internal torque is equal to positive 1,000 Newton meters. Okay, so the point is we have all this stuff going on. We have all these kinds of internal loads. But if we're just trying to calculate the stress tensor that's due to the tension, we're only going to use this one. Okay? And the stress tensor due to the tension is the same as it would be if this was the only load acting. Okay? So now the XX stress is equal to 1,000 divided by 0.001. This is newtons, this is meters squared. And so you get a value of 1.0 times 10 to the 6 pascals. Oh no, that's 6,000. I'm looking at the wrong one. Okay, so the internal tension was 6,000. And so if you divide that out, you get 6 megapascals. And so the stress tensor due to tension is 6.0 times 10 to the 6, and then zeros everywhere else. And well, this is just the stress tensor representing points on that line. On this, it's really, a cross section, but anywhere on that cross section, the stress due to tension and compression is the same. Any questions about that one? Okay, so that's all there is to say about this one. The other three now are going to be harder. Yep.
Was the rotational supposed to be 0.75 then? Because if you did it at the dotted line, because you only did 0.25.
But the whole thing is 0.5 meters.
Oh, okay.
So the dotted line is at 0.375. So I think that's one I actually got right. That's what you should do, is email me when one of these things is right. It'd be much more uplifting.
Do you have a special scan box for this class?
Yeah, it just goes right to that.
Keep on telling you like you got it.
Yeah, right. Okay, so the next one we're going to do is the stress due to bending moment. And the idea of how this works is the following thing. If you take a beam, let me draw it a little thicker just to illustrate this, and you put a torque on it like this, it's going to bend into a curved shape. And I'll color the bottom red and the top green. To celebrate the country Italy. Well, when you bend it like this, the top gets shorter. The bottom gets longer. And somewhere in the middle, since it's continuous, there has to be a line that stays the same length. That line that stays the same length is going to be an important thing for us. That's called the neutral axis. And so based on this, as you move away from the neutral axis downwards, in this case, the way I have, all this would be opposite if we applied the opposite bending moment to it. But the way I have it drawn, as you move downwards, are those elements in tension or compression? Tension. They're getting longer, so they're in tension. As you go up, they're in compression. Okay, so as you move toward the green, the lines get shorter, so compression increases. As you move towards the red, the lines get longer. So tension increases. And at the neutral axis, if there's no deformation, there's no stress. So what we're talking about here is X normal components of the stress tensor. The same direction as the tension and compression. So before we go into how to calculate the stress, we need to be really clear about when these calculations apply. I'm not going to go through the derivation of the formulas, but the derivation is based on some assumptions about the material that aren't true for every kind of shape. So let's think of these as required properties of the beams.
Question for you.
Yeah,
I don't know, maybe you just said it, but I was writing, so.
but I was daydreaming.
But at the initial
I was thinking about a more interesting class.
Yeah. At an initial axis, the only reason why there's no stress is because the magnitudes of the tension and compression are basically the same but opposite, right? And then you cancel each other out.
I think the easiest way to think about it is if you accept that this one's going to get shorter and you accept that this one's going to get longer. Somewhere in the middle there's one that doesn't change length at all. And so since all of these stresses are along the axis of the beam, that's not going to have any stress at the point where the length doesn't change. Okay, so required properties of beams for these calculations. And this is just for bending. This isn't true for the other types of internal loads. Only if you're going to use this approach for stress due to bending. So here is the column of things that we can do, and here's the column of things that we can't do. So the first requirement is the beam has to be straight or close to straight, nearly straight. So we can do beams like that, and we can get pretty good approximations doing beams like that. But we can't use this for calculating stress in things with really dramatic curvature. Second, the beams need to be prismatic. Or nearly prismatic. Which means that the cross-section stays the same along the length of the beam. So we can do beams like that. We can get good approximations for beams like that. But we can't do beams with dramatic changes in cross-sectional size or beams that are changing cross-sectional shape. Let me see if I can get this idea across. So say that it's circular at one end, and at the other end it's square. Okay. And then the last one is the cross-section needs to be symmetric about the vertical axis. I'll call it the y-axis. That's how we're always going to set it up, with the y-axis up or down. So this is a little surprising. We can use this for really complicated shapes as long as they're symmetric about the y-axis. Something like this. Say that's the cross-sectional shape, that's fine, okay, because it's symmetric about that axis. Question?
Couldn't you, rotate your axis?
That's an important question. No. We are doing, so when I say the vertical axis, what I mean is symmetric about an axis that has this relationship with the bending axis. So all these calculations we're doing are assuming that the bending is about the z-axis, and in that case, and the x is along the long axis of the beam. And so it's not really that it's vertical. It's not really being vertical that's important. It's the relationship between this axis of symmetry and the axis of bending. But that's a really important point. We can't do things like this. We couldn't do a cross-section like this. And let me draw, let's say that this is the bending axis. This is the bending axis. So we can do calculations for this one, not this one. If the bending axis were vertical on this second cross-section, then we could do it, because we'd have the proper relationship between the axis of symmetry and the bending axis. So here are the sort of take-home messages about these stresses. So notice the stress tensor due to bending has only an x normal element. That's the same as it was with the tension and with the stress tensor due to tension compression. Second, the value of that stress is equal to 0 on a line somewhere in the middle of the cross-section. And it turns out that that line in the middle of the cross-section goes through the centroid of the cross-section, passes through the centroid of the cross-section. Three, sigma xx gets more negative as you move toward the center of curvature. So the center of curvature, let's go back up to this picture of the curved beam. When you deform this, you get part of a circular shape, and that circle has a center. And that center of that circle is the center of curvature. So as you go closer to the center of curvature, the values of the stress get more negative. And then 4, you get more positive as you move away from the center of curvature. Okay, so the formula, I'll give you the formula now, and then we'll talk about the two mathematical definitions we need before we can use it. So sigma xx is going to be equal to negative bending moment times the value y divided by uppercase I. This I is called the area moment of inertia. And this y is the height of the desired point above the neutral axis. So before we can use this, we need two mathematical definitions. First, we need to know what the neutral axis is. And second, we have to define the area moment of inertia. Any questions about anything so far? Okay, so the first one is the neutral axis. This is a horizontal line through the centroid of the cross section. Parallel to the z-axis. So if this is the beam, the neutral axis is this direction. And we'll put our coordinate system origin at the centroid with x this way Okay, so x is along the beam's axis, y is up, and then z has to satisfy the right-hand rule. One thing to notice about the neutral axis is it's not really an axis at all, it's a plane, which is a little annoying. I mean, it's a two-word term, and half of the words are wrong. But we don't get to change that. It's been around too long. But so if you look at this, so given the direction of the coordinate system that we're going to be using, we have an x-axis that way, a y-axis this way. So this picture is in the xy plane, and the blue is the neutral axis. this picture, the cross-section is in the YZ plane, and it shows the neutral axis. And so the neutral axis is really a plane that you can see in either of those two views. Okay. So you can draw the neutral axis as a line in either the XY plane or the YZ plane. So if you extend the neutral axis in the x direction, along the beam's length, the neutral axis is really a plane. And under bending, this plane retains its original length. Along the x-axis. Yeah. Any questions about that, visualizing what the neutral axis is? So the next one that we need is the area moment of inertia. Mm-hmm. Yeah. That's right. There is a plane that slices this this beam in half, top to bottom, and that plane's length doesn't change as it bends. What? That was the blue line before, and it's the dark green line here. No. No, I refuse to do that. That's one step too far. I choose my colors based on what I find to be prettiest at the time. The area moment of inertia. This is a measure of how effective a cross-sectional shape is at resisting bending. The more area the cross-section has, located far from the neutral axis, the higher the moment of inertia is. We're going to use this capital I to represent the area moment of inertia. And so this is an important point. I know a bunch of you have taken dynamics already. Notice that deform and dynamics both have moments of inertia. And both of them are denoted capital I. And both use the parallel axis theorem. But those are two different quantities. So that's an easy thing to get confused about. In dynamics, what you have is the mass moment of inertia. And that measures an object's resistance to angular acceleration. In D form, you have the area moment of inertia. And that measures a cross-section's resistance to bending. A lot of people get confused, so you know, a good way to get sort of be known around your department or whatever is to insult people for being dumber than you. And this is a good way, because like you're going to see a lot of people who are going to confuse these two things, not notice they're different. It's an easy way to make someone feel bad about themselves and pump yourself up. Okay. Okay, so here's the integral definition of the area moment of inertia. The moment of inertia about an axis is equal to the integral over the cross-section of y squared dA where y is the height above the axis. And so you can see that if you're looking at, so take an arbitrary cross-section, you're just going from point to point on there and seeing how far that point is from the neutral axis. And you're just adding up all those distances squared. And so if you have a body that has a lot of material far away from the neutral axis, you end up with a big value of this IA. And then you also have something that's very good at resisting bending. Let's do this integral one time. But really, when we do this, we're just going to use formulas. So let's say we have a cross-sectional shape that's a rectangle. And it has a width W and a height h. The neutral axis goes through its centroid, so this is the neutral axis. I think orange this time. That's a lie. Okay, this is the neutral axis. So what we need is a system for defining these infinitesimal bits of area so that we can integrate over the areas. And when you're using these integral definitions to figure out a value, you know, these integral definitions come up in a lot of different classes. The key part is figuring out how to break up the element that you're integrating over. In this case, how to break up the area into infinitesimal bits of area. Since we're doing a rectangle here, I mean, if we were doing a circle, maybe you'd want to do it in terms of angle theta or something as you go around in little increments d theta. In this case, with a rectangle, I'm going to make the strips like this. Where the thickness of this infinitesimal strip is Vy. And then dA is just going to be, since this is a rectangle, it's just going to be W times dy. And then y is just this. The distance from the neutral axis to the strip. Okay, so the moment of inertia, the area moment of inertia about the neutral axis, is equal to the integral of y squared times w dy. So I just replaced dA in the definition with w dy. And then we're going to integrate this over the range negative h over 2 to h over 2. Those are the y values that represent this whole shape. And so we get w y cubed over 3 evaluated from negative h over 2 to positive h over 2. And you get w h cubed over 24 minus negative wh cubed over 24. Add those together and you get wh cubed over 12. So for any rectangular cross-section, where this is the width W and this height is H, the moment of inertia about the neutral axis is 1/12 WH cubed. And you can see that the height is much more important to the to the value of the moment of inertia than the width is. And you know that from just from experience. Think of trying to bend this calculator. You know, if you hold it like this and try to bend it down, it's relatively easy to bend. I could probably break it. You know, if you turn it like this and try to bend it, it's really hard to bend. That's because when you hold it like this, you have a high value of the moment of inertia. When you hold it like this, you have a low value. And that has to do with the W, the width being linear and the height being cubed. Any questions about that?
Is that why they do those kind of things in aircraft frame build? Like
Yeah.
look at the
Yeah, exactly. And it's why I-beams are the shape that they are. An I-beam has a very high value of moment of inertia given the amount of mass that's put into it. And that's what they're trying to do, is just make something that's resistant to bending.
So if you think about the I-beam,
Mm-hmm.
if you put the load this way, you have the vertical bar
Mm-hmm.
that prevents it, and then if you put it this way, then you have the true one.
That's right. Yep, that's right.
Is there a reason why the top and bottom horizontal, I guess, beams are
Mhm.
shorter than the vertical one?
The top and bottom, I don't know if that's, I think there's probably different dimensions. I don't know, though. I think there's probably different dimensions for different applications. I don't know if that's true. Do you know anything about that? I-beams?
Yes?
There's probably, companies make I-beams with different dimensions,
Oh,
I
yeah.
would imagine.
Oh, sure.
Yeah.
You're not going to have just, okay, here's one I-beam,
Yeah.
6 inches by 8
Yeah.
inches by 6 inches, and that's what you're going to use for.
But I would guess some are thinner this way
Oh,
and
yeah.
some are thicker,
Oh, yeah.
depending on
It's
the
like C
application.
channel.
Yeah.
I-beams are more like structures, and then I just, because of automotive applications, I see the C channels all the time.
Oh, yeah.
And you can't drill on the C channels on truck frames. C channels, you can't drill on the top. You got to drill only in the side when you attach things.
Yeah, yeah. And so all of those, all of those things are just, well, bending isn't the only thing they're trying to resist, but this resistance to bending is a big part of how any kind of structural element is designed.
What about the twisting?
That's, we'll talk about that later.
Isn't that the
That
torque?
uses a different, that's the torque, when we get to the torque, yep. And that has its own parameter that defines how easy an object is to twist, unrelated to this. So, okay, let's take a 10-minute break, come back at 2:12, and I'll keep going. Okay, so we talked about the rectangular cross-section. The only other kind that we're going to use is a circular cross-section. So if you have a beam that's a circular cylinder with a radius r, the neutral axis goes through the middle, and the moment of inertia about the neutral axis is pi r to the 4th over 4. And the SI units for moment of inertia, for area moment of inertia, are meters to the 4th. There are two things these formulas just give you the area moment of inertia about the neutral axis of that shape. But there's two things that make this more useful, make it so that we can use these two simple shapes and build up more complicated shapes like an I-beam or whatever. So two things make these formulas more useful. The first one is you can add moments of inertia of simple shapes to find the moment of inertia, to find I for a complicated shape. So what I mean is, for example, bless you, if you have an I-beam, you can, bless you, you can break that up into 3 rectangles, calculate the moments of inertia of those, and add them up. In order to do that, though, you need to know the moments of inertia of those smaller rectangles, those component rectangles, about the neutral axis of the whole shape. So you have to be able to change the axis. So to do that, you need to express these individual I values about a new axis. And that we'll do with the parallel axis theorem. So the second useful thing is it follows a parallel axis theorem. That says the moment of inertia about some axis A is equal to the moment of inertia about the neutral axis plus the area of the shape times d squared, where d is the distance between the neutral axis and A. And it's called the parallel axis theorem because A and the neutral axis have to be parallel for this to work. Okay. Well, let's do it. This doesn't look so bad. So let's say that we have an I-beam. That's made out of 3 rectangles. The thickness everywhere is 1 centimeter. This is a huge I-beam. So 0.01 meters is the thickness. That's also the thickness of the web. This thing in here is 1 centimeter. This is 0.5 meters. This is 0.5 meters. the neutral axis goes through the centroid, and the centroid lies on any axis of symmetry, which means the neutral axis is that. That's the neutral axis of the whole shape. So what's the area moment of inertia of this I-beam about its neutral axis? Okay, so I'm going to break it up into this rectangle and this rectangle and the bottom one. So the first rectangle. So first we have to calculate its moment of inertia about its own neutral axis using the formula. And then we have to use the parallel axis theorem to represent, to calculate the moment of inertia of rectangle 1 about that red neutral axis of the whole thing. Okay? So the moment of inertia about the neutral axis is equal to 1/12 times the width. What's the width? 0.5 times the height cubed. What's that? Yep, 0.01 cubed. And then we're going to use the parallel axis theorem. So what's the distance between the neutral axis of rectangle 1 and the whole shape's neutral axis? 0505, that sounds right to me. No. 0.2, right. 0.255. Yeah, 0.255. So we have the area of the whole shape, which is 0.01 times 0.5, and then we're multiplying that by 0.255 squared.
What's the thickness again? 0.01?
0.01. So half the thickness is 0.005. So 0.25, yeah. Okay, and here is why an I-beam works so well. Look at the moment of inertia of that top rectangle about its own neutral axis. It's tiny, right? It has almost no contribution at all. But then when you add it to look at how big the parallel axis theorem contribution is. The contribution from taking that thin rectangle and moving it far away from the neutral axis, that's where all of its resistance to bending comes from. So what do you get for this one? Let's do these separately just so you can see that. So this is 1 times 10 to the minus 6, 0.5 times 10 to the minus 6, and then divided by 12. What do you get there? It's like
4.16 e to the minus 8.
4.16. That's repeating, I think, e to the minus 8. So it's very small. Basically nothing due to the shape itself. But now the parallel axis theorem part, what do you get for that? Minus what?
Minus 5.
4 or 5? 4. Okay. And so altogether, you basically get, this one is just insignificant. You just get 3.25 times 10 to the minus 4 meters to the fourth. Then rectangle 2. The moment of inertia, the neutral axis of rectangle 2 is the same as the neutral axis of the whole shape. So this is just equal to 1/12 times the width of 0.01 times the height of 0.5 cubed. And what's that equal to?
Very small. 1.042 e to the negative 4.
Okay. And then rectangle 3 is going to be the same as rectangle 1 because so rectangle 3, the moment of inertia about the neutral axis. It's the same rectangle as the top one, so the moment of inertia about its own neutral axis is the same as it was before. And then it has the same area, and you're moving at the same distance from the neutral axis of the whole shape. So 0.01 times 0.5 times 0.255 squared, and you get the same thing we did before, 3.25 times 10 to the minus 4. And so all together, you get 7.59 times 10 to the minus 4 meters to the fourth. Any questions about that? Okay, so now that we have those mathematical definitions, finally we can calculate the stress. Stress at a point due to internal bending sigma xx is equal to negative my over I. Where m is the bending moment, is the internal bending moment. I is the area moment of inertia about the neutral axis. And y is the height of the desired point above the neutral axis. So that means if the point you're looking at is below the neutral axis, then y is negative. Well, let's go back to the example that we used in tension compression. Where's that thing? Okay, so this example, what do we get for the bending moment? $31.25. So at the dotted line, the bending moment was equal to 31.25 Newton meters. So the x so let's give that a we need to give that a cross section. So let's say the cross-section of the beam is .2 .005 That works, right? Well, this makes more sense. Let's do it as 0.1 and 0.01. What? Yeah. This beam. Where is it? So this beam, but the cross section is this, and I think that comes out to the area that we said before. And let's calculate the stress here, here, and here. So the first thing we have to do is calculate I. So the area moment of inertia about the neutral axis is 1/12 times the width, 0.01, times the height cubed. So what do you get for that? .3 times 10 to the minus 7 meters to the fourth. at the top, the x normal stress is equal to negative internal moment, so 31.25. What's the times y? What's the y value for that green line at the top? 0.05, yep. And then divided by I, 8.3 repeating times 10 to the minus 7. And what do you get for that? Thanks, Louie. No thanks to everyone else for doing nothing.
I got a negative value.
Yep, you can get negative values.
Minus 1.88 e to the minus 8.
Wait, it should be a big positive number. Did you do a 7 here?
I'll put it in again.
E to the 6th. Negative 1.88 times 10 to the 6. Pascals. Okay, so what that is saying is, at this point, we know it's a positive bending moment, which means that at that point, there's a curvature like this way, you know, like a smile. And so, as you get closer to the center of curvature, so as you go up, the elements are getting shorter, so they're in compression. And that's what that negative stress means, that the point up at the top is in compression. What about at the middle? 0, yeah. Y is equal to 0 at the neutral axis. So the XX stress is equal to 0. At the bottom, that's right. All that changes is the Y. It's the same magnitude, but it's negative. So you have sigma XX is equal to negative 31.25 times negative point, how big was it? 0.05 divided by I, 8.3 repeating times 10 to the minus 7, and you get a value of 1.88 times 10 to the 6 pascals. So this is compression at the top. This is tension at the bottom. And now we can put those in stress tensors. At the top, the stress tensor due to bending is equal to negative 1.88 times 10 to the 6. 0, 0, 0, 0, zeros everywhere. And at the bottom, the stress tensor due to bending is positive 1.88 times 10 to the 6. 0, 0, zeros. If we add the stress due to tension and the stress due to bending, let's do it just once at the top. we get a new stress tensor that's equal to, what do we have up here for tension? We had 6 times 10 to the 6. So 6 times 10 to the 6 with zeros everywhere else. And now at the top we had negative 1.88 times 10 to the 6. And so we get a value of positive 4.12 times 10 to the 6. Zeros everywhere else. Okay, that's at the top. Now what about at the bottom? At first thought, you might think it's just going to be the negative of that, because with bending we didn't, all we had was switching the values from the top and bottom. But remember that at the top and the bottom, the stress due to tension compression is the same. And so you're going to have this effect pretty often where at the top you have addition of the, at one side you have addition of the elements due to tension, compression, and bending. And on the other side you have, they're sort of canceling each other. So we're going to get a bigger absolute value at the bottom. So at the bottom, the stress tensor due to tension plus stress tensor due to bending is equal to 6 times 10 to the 6 and zeros. Plus positive 1.88 times 10 to the 6 and we get 7.88 times 10 to the 6 and zeros everywhere else. Okay, so what this says is, based on these two things, we're more concerned about what's happening at the bottom of the cross-section at this point than we are about what's happening at the top of the cross-section. This is the bending and the tension compression are the only two internal loads that produce normal stresses. And so this is actually the final answer for the normal stress in the x direction for the internal loads of the beam. So the next stuff we're going to do is going to deal with shear stresses only. Only the tension and the moment contribute to that normal stress. I'll write that. So only T and M contribute to sigma XX. The shear stress is going to contribute to sigma XY, and the torque is going to contribute to, well, a bunch of stuff depending on where you look on the cross section. But it's all going to be shear stresses. Right. Yep. Okay. Any questions? Let's stop there.